Hello, good morning, guys. How are you today? Can you hear me? Hi, Michael. And can you see my screen? Okay, so let's start our lecture today. Today lecture we will know or learn how to design structure steel frame columns, or mainly the members under combined axial loads and bending moments. So in the previous weeks, we have learned how to design members under axial loads and member under flexure. And today uh, we will have the members under combined axial load and bending moments, which is mainly in the frames columns. Okay. Okay. So this week we will learn about the second order effects and how to account for the second order effects using the moment amplification factor method, and we will be able to design beam column members, or what we call the frame columns subjected to combined loading. So now let's have a look on our slides today. So we have lecture 6. Can you see the slides now? Okay, so today our sixth lecture, and it will be designing the frame columns. The frame columns are mainly under axial loads and bending moments. Okay, so we have learned before how to design column under axial load alone and members under bending moment alone. So the third part would be combination of both. Okay, so after this week, you will be able to know the second order effects. We will see now what does the second order effect mean, and to be able to calculate the design moments, M M asterisk, with the moment amplification factor method. So actually we will have amplification factor, or trying to increase the design moment due to the second order effect. So this is how it works. We have already design moment, but actually due to the second order effect, we will need to increase the moment and the design for the increased moment. And finally, we will be able to design the beam column members, or the frame columns subjected to combined loading. Combined loading are again axial and moments. And we are using AS 4100 in, as usually, for steel members designs. Okay, so let's start our first part. Our first part is the second order effect, or B delta effect. So we have B delta effect. So this slide, we will have an example to see what is the B delta effect and how it affect our design, and we should consider it in our design. So if we have a column, fixed column, this fixed column is free at the top end and fixed here, and this column length or height is L. The column under axial load B or vertical load B. This force B in the direction of the member, so it is axial. And we have H is lateral load. The lateral load will lead to, or will cause moments on the column. So we are looking now on the moments. So the moment of this H will be M1. So H times L is our moment here. So M1, this is the reaction. But if we cut here at section 1, so we have H times L. So we have a moment here, M1 equal to H, the force, times the distance L. So this is M1, and the moment here at this point, section 2 is 0. So we have 0 here, M1 here, and connect with a straight line. But actually, due to the axial load, the column will start buckling. The buckling value in this case is small delta. So delta is the buckling or lateral buckling due to the applied loads. So this buckling will affect the moment, because actually when the column buckle, we have now another force that will cause moment. So B will add some moment on the column, or add additional moment. Yeah, we can call it add some moment on the column. This column is additional moment on the column. So we need to consider the additional moment. How much is the additional moment? The additional moment is B times delta. So the additional moment will be M additional equal to B times delta. So now the moment in this case is not M1, it is M2, where M2 bigger than M1 due to the additional moment. Okay, so now the B delta effect will cause, or we need to consider it in our design by increasing the moment or adding an additional moment to the column. So if your first order design moment is M1, so the actual design moment considering the second order effect should be M2, where M2 is bigger than M1 by the value of the B delta effect. Okay, do you have any question about this part? Okay, let's proceed. So this was an example for a column fixed and free at the top. Let's have a look on the columns in a frame or beam column member. So for second order effect on beam column members, the column in this case is under, we can call frame column. So the column in this case is under axial load and bending moment, as you can see here. So we have B and M. So if this column under B and M, this is how the deflected shape will look like for this beam. So we have first order deformation and second order deformation. The second order deformation is from the effect of B delta effect. That's why we call it second order effect. Just to receive a question. Is delta a force? A value? Delta is deformation. If we go back to the previous slide, delta here is the buckling or deformation due to the applied force. So the force is B, delta is deformation or deflection. Actually, we call deflection only on the vertical deformation. So this is lateral buckling or lateral deformation. So delta here is lateral buckling, not a force. Okay, so let's proceed now. We have second order deformation, which is the delta effect due to the buckling of this member. So we have like initial buckling, and due to the initial buckling, the buckling will increase to another by another value. The difference between those is delta or B delta effect, sorry. So for example here, if we have moment on this column M, so the initial shape for the moment is from here to here. Let's call it M, and from here to here M, and then this should be the initial value. Okay, but due to the buckling and the B delta effect, we have some additional moments. This value is our B delta. So B delta, B multiplied by delta is a moment, additional moment. Okay, so this in case of what? Moment uniform on the column. If the moment is uniform, means when you draw the moment alone, the value of the moment here M, the value of the moment here M, due to the shape of the moment we have. We have uniform moment. This one case. Another case for the moment on the column is non-uniform bending. So another case for B delta effect or the second order effect is B delta effect for non-uniform bending. Same case, but just the difference is we have a still B axial load on the column, but the moment in this case are in opposite direction. So if you draw the moment on this one, the moment should be something like this. So if this M2, this is M1, so this is non-uniform bending moment. Okay, so now when this column buckle, when the column buckle, we have first order deformation and second order deformation after buckling or due to buckling after delta. Okay, and the buckling in this case due to the moment will be double curvature. We call this double curvature because it is bent in two direction. Here it is single curvature because it buckled only in one direction. So here, due to the buckling, how the moment will differentiate from here to here. This is the moment diagram after the B delta effect is considered. So the moment will be here as we have M2, here M1, and here is the initial shape of the moment. Due to buckling, the moment will be second order or from parabolic. Due to the B delta effect accounted for. Okay, so now do you understand now the importance of the second order effect? The second order effect means that we have additional moment B delta should be considered in design. This is the main idea of the second order effect. Okay, so this is the concept. Do you have any question about the concept, guys? No? So now let's see how the standard, Australian standard AS 4100 consider this in design. So section 4.4.1.2 highlighted the second order effects and how to be considered in the design. So second order effect in section B 4.1.2. I just received a question. What will happen if we have different load and moments on both sides? What do you mean by different loads? From equilibrium, guys, if this B, this should be B. Because summation Y, forces in Y should be 0. Okay? So the columns or our members are under equilibrium. So the forces cannot be different. Okay? So B delta effect, we have one B and one delta. Thank you. So now let's return back to our second order effects. The standard asks to allow for effects of the design loads acting on the structure due to their deformed configuration. So to take the second order effect into account, we need to follow one of the two methods here. But we will be using only the first one, first order analysis with moment amplification in accordance with clause 4.4.2, provided the moment amplification factor delta B or delta S are not greater than 1.4. So actually, we have two methods for second order effects, but we will focus only on the first one, which is using the amplification factor in clause 4.4.2. But the method has limitation that the factors are used should be not more than 1.4. So delta B and delta S should be less than or equal to 1.4. This is the condition for this method. So in your design, if you are designing in real life, you should check this value, otherwise you have to use a different method, which is the second method, second order elastic analysis in accordance to Appendix E. Okay, so let's have a look on the first one here, A, which is the first order elastic analysis. So in this method, changes in the geometry are not accounted for. The changes on the effective stiffness of the members due to axial load are neglected. So the standard give us some ideas about how the method works. So the effects of the second order analysis on the bending moment shall be allowed for using one of the method of moment amplification factor in clause 4.4.22 and 4.423, except that where the amplification factor calculated in accordance is greater than 1.4. So repeating the same uh, part again. So we are calculating using amplification factor, which means that the design moment, M asterisk, should be increased to account for B delta effect. So we will not go to find how much is the B delta effect, or we don't need to calculate delta. What we will do, just follow the standards procedure to find an increased moment to design for. The increased moment is our new design moment, MM asterisk. So this means our design moment will not be M asterisk, it will be MM asterisk. MM asterisk accounts for the B delta effect. This is a summary of the method, and this is what you should do in your design. So just find the amplified moment or the increased moment. So let's now start learning about the method or how to find the amplification moment. So we have two type of members, braced columns and sway column. So if we look to any frame, if this is our frame, if we have two frames like this one, the frames may be under lateral loads and vertical loads, whatever the vertical loads are and the lateral loads are. We may have two type of frames or columns. The first one is braced, second one is sway or unbraced. What is the difference between braced and unbraced? Braced means the column are prevented from lateral deformation. So this means when you apply the lateral load, in this case, no lateral deformation of the column at the top end. So we prevent the movement of the beam here or the rafter, so the column will not be able to sway. In this case, we call the column braced. So the column will be only allowed to one deformation, which is, for example, buckling like this. So the column can only buckle, but no sway. So this here is delta small or buckling. In other type of columns or frames, the column is not prevented from move laterally because we don't have any support for this member, the beam or the rafter. So what will happen when you apply this load? The column will move laterally. So this is the new member location. So what is this movement named? This movement is delta capital or sway. So actually what happened to this column? This column will have two movement. The first one is sway, delta, and another movement which is buckling. So it has both of them. So this column here only under buckling, this column here under buckling and sway. So this is the difference between the two types of column. So this column here under lateral deformation, sway, and buckling. So under delta and delta, delta capital and delta small. So that's why the standard give us two procedure when we are calculating the amplification moments, because the braced member different from the sway member, as you can see. So let's start with a braced member. So this member, no sway will happen, no sway occurs. So the moment amplification factor for a braced member according to this clause for a braced member with zero axial force or braced member subjected to axial tension. So this for zero axial or axial tension. The design bending moment M asterisk should be equal to M asterisk M. So M asterisk M again, we mentioned this is the amplified or the increased moment. How can we find M asterisk M? For a braced member with design axial compressive force N as determined by the analysis, the design bending moment shall be calculated as follows. M asterisk equal to delta MM. So what this means? This means that for tension member or for member under tension, M asterisk M will be equal to M asterisk M. This means no amplification, or the amplification, the amplified moment equal to the original design moment. But for member under axial compression, M asterisk M should be delta B times MM. So here we have amplified moment amplified by delta B. Here delta B is 1 or no amplification. Okay? Where, how to find delta B? Delta B is calculated using this formula here for braced member. Delta B equal to Cm divided by 1 minus N asterisk divided by NOMB. Should be more than or equal to 1 because this is increased factor or increasing factor or amplification factor, so it should be more than 1. Okay, so to find delta B, we need Cm, N asterisk, and NOMB. We will see now how to find these values. So let's start with what is NOMB. NOMB is the elastic buckling load determined according to clause 4.6.2 for the braced member, buckling about same axis of the bending moment, design bending moment, M asterisk. So this means NOMB is the buckling load. So NOMB is the buckling, elastic buckling load, or what we call Euler load. If you study mechanics of material, so we have Euler load. Euler load by squared E I divided by K effective L to the power 2, where K effective L is the column buckling length. Okay, so we can easily find NOMB if we know E I, which is Young's modulus of steel. I, so E, Young's modulus. I, inertia of the member. Okay. And KE is the member effective length factor. We will see now how to find it. L is the member length from center to center. So if you know all of these parameters, you can know NOMB. So if we go back to our calculation, we know how to find NOMB. So what is the next parameter to find? CM. So for a braced member subjected to bending moments only, the factor Cm shall be calculated as follows. So for Cm equal to zero point 0.6 minus 0.4 beta m should be less than or equal to 1. So this is the value of Cm, but one condition here for members, braced members subjected to end bending moment only. So what this means that the column here under end moments only. M1 and M1, for example, or M1 and M2. So you can use this formula here. Where beta M is the ratio of the smaller moment to the larger bending moment at the end of the member, taken positive when the member is bent in reverse curvature. So what this mean if we add this here as well? So we have two cases, beta m equal to beta m equal to if we have m1 and m2, and here if we have m1 and m1 m2, sorry. So we have two cases. When we have the two moments, sorry. The first one, when they have the moment m1 and m2, the standard mention, if you go back, beta m is the ratio of the smaller moment to the larger moment. Okay? So we'll assume that m1 is smaller or larger. What do you think? Michael and student who have studied steel and timber before, which one is M1, which one is M2? Smaller is M1 or M2? Do you remember? So smaller is M1. So this means larger is M2. So this is how we assume the moments. We assume that the smaller moment is M1, larger moment is M2. So beta M means M1 over M2. Okay, generally we assume M1 is the smallest, M2 is the largest. So you will find beta M equal to M1 over M2. But now we need to decide the sign. So the value is okay, but the sign. The sign is, if we go to the standard here, based on the curvature of the bending. So taken as positive when the member is bent in reverse curvature. So what this mean? If we look to the curvature of this moment, when you bend this one, so this is single curvature. Here, for the other case, we have one moment bend in this direction, one moment bend in this direction, so it will bend like that. So this is double curvature or reverse curvature. So in both cases, the value is m1 over m2. But the standard mentioned that for reverse curvature, you can take it positive. For single curvature, take it as negative. So this means we take the sign negative for single curvature. We take the sign positive for double curvature. This is how to link the sign with the curvature of the member. Okay, so now if we know beta m, we can know Cm. If we know Cm, so we can find delta B. Because in asterisk, we already know the design axial load, so we know also in asterisk. So now we can find delta B. Delta B is the amplification factor to find the design moment. The only condition we have, delta B should be less than or equal to 1.4. Can't be more than 1.4. Okay, so all of that was for what? Braced member. Now for sway member or unbraced member. For unbraced member, the method mentions that the design bending moment will be m asterisk equal to delta m times mm. So in this case, we have delta m, not delta b. So delta m for a sway member, delta b for a braced member. Sorry, delta m for sway member, delta b for braced member. So now, how can we find delta m? Delta m is the greater of two values. So you have to find two values and select the greater of these two. So we have delta B and delta S. So delta B is similar to what we have calculated in the previous step, which is delta B equal to, what was the formula here? Cm divided by 1 minus n asterisk divided by NOMB, and should be more than 1. Then you need to find delta S, which is the moment amplification factor for a sway member. Determine as follows using the formula delta S equal to 1 divided by 1 minus 1 divided by lambda ms. So the only parameter we need to find here to find delta S is lambda ms. Lambda ms is the elastic buckling load factor determined according to clause 4.7.2.2. So now how we can find lambda s? This is the next slide. So lambda s is the, as you can see, lambda s is not for one column. Lambda s for each story, for story, not for column. So if you have frame, again, if this frame under sway, so we are not considering one column. We are considering one column, two column. So that's why the formula lambda s equal to summation NOMS divided by L divided by summation N asterisk divided by L. So this is our formula. So sigma means for the number of columns you have per story. So we will divide the buckling factor or the buckling load for each column over its length and get the summation and divide by the design axial load for each column divided by its length and take the summation. So this is how lambda s is calculated, where n asterisk is the member design axial force with tension is taken as negative. So this one important note here. These formulas are positive for negative for compression and negative for tension. Okay, and the summation includes all column within a story. So if you have two columns, take all two. If it are three or four, you have to consider all the columns. The elastic buckling load again, similar to before, NOM. We have just illustrate this earlier. Same clause, NOM equal to this Euler load by squared EI divided by K effective L all squared. So if you know NOMS and N asterisk, you can find lambda MS. If you find lambda MS, you will be able to find delta S. So if you know delta S and delta B, you can find delta M. So you can find the amplified moment M asterisk. Okay? Do you have any question, guys, about that? No? So now what is the missing parameter here? The missing parameter in our calculation is the buckling factor K effective. How to find the buckling factor K effective? For frames, we can't use the ideal values for frames. I just open the standard for you now. Okay, if we open the standard, here is the member effective length factor KE using this table. But this table is only for idealized condition. So it is like simplified method or approximate method to find KE. I think most of you know this part, but in our course, because we are designing frames, so we can't use the ideal lens, but effective lens factor. We should use the curves or the charts we have here. So the member effective lens factor, KE, will be calculated using these two figures. This figure for a braced frame, which is figure 4.6.3.3 in the Australian standard. One for braced frame A, and B for sway frames. So if we look here, how to enter this table, or sorry, how to use this chart, we should know the stiffness end ratio for the top end or end one, and the stiffness ratio for end two. So if we have a column, this column is braced. So we have gamma 1 at the top end, for example, gamma 2 at the bottom end, for example. So we should find gamma 1 and gamma 2. If we find gamma 1 and gamma 2, easily we go to the chart. For example, if gamma 1 is 1.2, so you go horizontally. And if we have gamma 2 as well, 1.2, this is just an example, guys. So they intersect here. So how much our K effective, for example? So K effective equal to 0.8. So this is the exact method or the method we are using for frame columns. And similarly for sway members. So for sway member, again, you need gamma 1, gamma 2. If gamma 1 and gamma 2, 1.2 here as well. So let's quickly do it. So this gamma 1 and this gamma 2. So as you can see, the value here is not 0.8 because it is a sway member. So K effective here is almost 1.4. Okay, so we can take it 1.4 or 1.38 for example, because it is very close to 1.4. The idea is we need to know gamma 1, gamma 2 to find K effective 1.4. So now how to find gamma 1 and gamma 2, which is enclosed 4.6.3.4, the stiffness ratio for rectangular frames or frames columns. So the formula is gamma equal to summation I over L for columns divided by summation beta effective I over L for beams. Okay, so if we have column of a frame, let's assume that we have column in something here. We are calculating for this column. So the column is connected to beam 1 from right, beam 2 from left, and we have also column 1 here and column 2 here. This is a general or a generic case. So if we are calculating gamma 1 here. So gamma 1 here should be summation I column 1 divided by L column 1. No, just to remove the summation now. Because how many columns we have? Two. So we have I over L for C1 plus I over L for C2. Divided by how many beams we have? Two beams. So divided by beta effective for B1 times I over L for B1 plus beta effective for B2 times I over L for B2. Okay, so we look at how many columns and how many beams connected at the end so that we can find the value of gamma 1 or gamma 2. So if we look back here, we know this one and this one, summation I over L, summation I over L, and the standard give us exceptions for compression member whose base is not this for the base. So for members connected to beams and column, this is the formula. For base, which is this part here, we have two cases for base. The first case, for base is not rigidly connected to the footing, the gamma value shall not be taken less than 10. For member whose end is rigidly connected to footing, gamma should not be less than 0.6. Okay, what this mean? The base can have two options or two cases. Not rigid means bend support or hinged support. So for hinge, gamma equal to 10. The other case is fixed or rigid. So in this case, gamma 2, as the standard mentioned, 0.6. So for bend, gamma is 10. For rigid, or sorry, for fixed or rigid, gamma is 0.6. This is given in these two exceptions here. Okay, so now we know everything except for yet beta effective. How can we find beta effective? Beta effective is the modifying factor for beams account for the condition of the far end of the beam. As in table 4.6.3.4, the modifying factor are as follows. So the fixed end condition at far end of the beam can be bent or fixed or rigidly connected to a column. Okay, we have two cases, one case for braced, one case for sway. What this beta effect means first, beta effective means if we look to our explanation here, we didn't consider what is the support on the other end. So this will be considered by beta effective. So for the beam, if we are calculating gamma here, gamma 1 here, so we should look to the ends at if this B1. So we should look to the end at the other end. So this end can be hinge or bend, and another case, this can be fixed support. Another case, we can have a column. So this gamma 1 we are calculating for this one and this B1. So this B1, this B1. So the first case is hinge. Second case is fixed support. Third case is a column. So A, B, C. The standard mention, if the other end of the beam B1 is hinge, it can be 1.5 for beta effective will be 1.5 or zero point 0.5 based on column braced or unbraced. Okay, so we can give this case A, this case B, and the middle is case C. So when you are calculating gamma for one column, top end of the column, and you are looking at the beam, you should look to the other end of the beam. It can be hinge or fixed or rigid connected to a column. Okay, are these cases okay? No problem? Okay, so any question about this part? So if we know beta effective here, we can find gamma. If you find gamma, so you can find K effective based on the column braced or unbraced. If you know K effective, you can find NOMB or NOMS based on the calculation. Okay, do you have any question, guys, for this part? So all this part was the second order effect and the amplification moments. So we will have a short rest for 8 minutes and we can meet at 10:15. Is that okay? So we have short break. We can be back at 10:15 a.m. Thank you. What does it mean? The beam restraining a braced member? Yeah, this what it means. If this column is braced or unbraced, because we are designing or finding the value for this column. So this column can be braced or unbraced. So if it is braced, you go to this table, this column. If it is unbraced, you go to this column. Okay, thank you. So where is the break? So see you in 6 minutes. Okay, guys, let's continue our lecture. So second part of the lecture is to design the frame columns under combined action. So this is covered by section 8 of the standard AS 4100. So the section in this part is column or beam column section, which is member subjected to combined axial and bending moment. Okay, so we will have to check the design action in combination of nominal section and member capacity. So we will need to check the nominal section and member capacity for the columns because, as you know, axial members under compression. So under compression means under buckling. So under buckling means we have section capacity and member capacity. The design action in this part are the design axial force in asterisk, And we may have design bending moments about X and Y. So if we have a cross section, so this is Y axis, this is X axis. So this column can be under axial load and asterisk, and we may have mx asterisk, and we may have my asterisk. So we have n asterisk, m asterisk x, and m asterisk y. Okay, where x, as you know, what is x-axis? X-axis is our major or strong axis of the section. And y is the minor or weak axis. So for each section, we have x-axis as major axis and y-axis as minor axis. And we can have moment about both axes or moment about one axis. So we have many cases. That's why this part we are covering the cases that may have. The first one is members under uniaxial bending. What uniaxial bending mean? Uniaxial means we have only one moment. So uniaxial bending mean we have only one bending moment, can be about x, mx, or can be about my, my. Plus, what we have else? Axial load in asterisk. So you can have either mx with n or so n asterisk with mx and 2 is n asterisk with my. So this two cases. So the standard will check first the section capacity. So we have to check section capacity under section 8.3. So section 8.3 will check the section capacity. For first case is the uniaxial bending about the major or principal axis, major principal axis. So in this case, we have n asterisk and m asterisk x. Okay. Also here, one note is for section capacity, the compression and tension member will be dealt similarly. So if we have same formulas for both, I put it here, compression and tension. If they are different, so we separate them as the standard did. So we are following the standard. So for uniaxial bending about major axis, the design moment mx should be less than or equal to phi mrx. So before it was msx if we have only axial moment, sorry, if we only have bending moment. Now it become phi mrx. So phi is the capacity factor. For steel members, we mentioned that phi equal to 0.9. So no problem with phi. But now, what is mrx? mrx is the nominal section moment capacity reduced by axial force, tension, or compression. So MSX was the nominal section capacity. Here, MRX is section capacity, but reduced by the axial force. So here, as you can see, MRX should be equal to MSX, the nominal section capacity, nominal section capacity calculated before in the flexure member design, reduced by the axial force. So you should know in asterisk the design axial load, and NS, which is the section capacity for axial. Okay, what is the trick here? The trick here is this sign is what? The sign is negative for compression force, positive for tension force. Because the tension force will increase the nominal section moment capacity for the member because you are reducing the compression. So just be careful here in this formula. The negative sign is for compression and the positive sign for tension. Okay, alternatively, for doubly symmetric I section or square hollow section, when the section is compact. So if we have a compact section, we may have another formula or another option is to find MRX using one of the cases we have. So if the section is compact, MRX can be using the first case here when KF is 1. So for KF, the form factor is 1. We can have MRX equal to 1.18 MSX multiplied by 1 minus N asterisk divided by phi NS less than or equal to MSX. So this only for KF equal to 1. What if KF less than 1? So if KF less than 1, this case here, so in this case, MRX will be found using this formula here. So it will be MSX 1 minus N asterisk over phi NS multiplied by 1 plus 0.1882 minus gamma W, sorry, lambda W divided by 82 minus lambda WY, where lambda W and lambda WY are the values of lambda effective and lambda effective yield for the web. So this was lambda was the cylinderness limits for the web. Okay, so this is the first case for N and MX. The second case for members under uniaxial bending about minor principal axis y-axis. So we have N asterisk and M asterisk Y. So when uniaxial bending occur about the minor axis, the design bending moment shall satisfy the following. So instead of phi m r x, phi m r y, where phi is 0.9. And phi m r y, sorry, r m m r y is calculated using the formula MSY 1 minus n asterisk over n phi ns, where again biaxial or compressive force. This sign here, sign is negative for compression force and positive is tension force. Okay. Another way to find MRY using the following formulas. For doubly symmetric eye section, when the sections are compact, so this for compact sections, MRY shall be calculated using this value. So it is quite close to the previous, but 1.19. If we go back here, it was 1.18 for X. For Y, it is 1.19. But another difference here is here the bracket is not squared. Here the bracket is squared. Anyway, this is the formula for symmetric eye section. Okay. If it is square hollow section, you can use this formula here, similar to before. So for eye section or symmetric eye section, if this section is compact, so you can use this formula here for MRY. Okay, so the next part is if the section is under biaxial bending. What is biaxial bending means? Biaxial bending means our column, this is the plan view of the column, and this is y-axis. This is x-axis because x is the major, y is the minor. So this column under one moment mx asterisk and one moment about y my asterisk plus n asterisk in the middle. So biaxial bending moment. N asterisk, mx, and my asterisk. So if the column under n and mx and my, the section capacity for this member, for tension and compression member, is following clause 8.4, 8.3.4. So where the biaxial occurs, bending occurs, the design tensile or compressive force N and the design bending moments about major and minor axis shall satisfy the following formula. So here we have a formula that include the three straining actions. So we have N asterisk divided by phi ns, this for axial, plus M asterisk x divided by phi msx plus m asterisk y divided by phi msy. All of this should be less than or equal to 1. So we are considering all the string action in one formula here. Alternatively, we can, for doubly symmetric I section and rectangular square hollow section, if the section is compact again, you can use the formula here for compact section. So in this formula we have mx asterisk over phi mrx to the power gamma plus m asterisk y over phi mry to the power gamma should be less than 1. So in this formula we have the moments only because gamma will consider the axial load. So gamma shall be calculated use this formula. Gamma will be equal to 1.4 plus n asterisk divided by phi ns, and this value should be less than or equal to 2. So if we know gamma, we can know we can check the moment mx asterisk and my asterisk using the formula above. So this for section capacity for biaxial moment. So if we go back, we have 3 cases for section capacity. One of them is uniaxial with major axis n and mx. The second is uniaxial about minor x n asterisk and my. And the third is biaxial, which is n asterisk, mx asterisk, and my asterisk. So we have the 3 straining action. Now, what is the next step after the section capacity? We have the member capacity. So member capacity, we consider here in this part the global buckling behavior. And again, we have cases of uniaxial and biaxial. But here, because what is your understanding about the global or the member capacity? The global or member capacity is a problem for compression member. So tension and compression member can't be dealt the same for global buckling behavior. So that's why we have compression member alone and tension member alone. So the first case for uniaxial bending, and we have 2 cases for uniaxial bending. One of them is in plane and out of plane. So for in plane compression member, the member bent about a principal axis shall have sufficient in-plane capacity to satisfy the following. So in this case, M asterisk should be less than phi mi. So in plane capacity usually means the member is bent about its major axis. Okay, so this is the member capacity for member bent about its major axis. The design moment should be less than phi mi, where m asterisk is the design bending moment about the principal axis, and phi is the capacity factor. Phi in this case is 0.9. Okay, MI is the nominal in-plane member moment capacity. MI in this case, as you can see, calculated using the formula MS times N1 minus N asterisk divided by NC, where MS is the nominal section capacity determined in accordance with clause 5.2 for bending about the same principal axis as the design bending moment. So MS is the section capacity of the member of bending moment, similar to our design of flexion member before. Okay, N asterisk is a design axial compressive force. NC is the nominal member capacity in axial compression determined according to clause 6.3. So NC is the member capacity in axial compression as a column under compression. So it is like mix of the section capacity of moment and member capacity of compression. For tension member, because tension member, we are not worried about no global buckling problem from axial loading. So for tension member under uniaxial bending, the member capacity shall satisfy similar to clause 8.3, which we have done earlier here. So for if the member under major axis, major bending moment, or x bent about its major principal axis x, so it's following same formulas here. So what I have done is just copy it again. So for tension member, there is no problem with the member capacity because it will be as same as the section capacity check we have done earlier in clause 8.3.2. So you will have mx less than phi mrx and phi mrx calculated as this formula here. Okay, so our worry here is not the tension force. Our worry here was the compression force for this part. This for in plane or bent about major axis. The second type is out of plane. Out of plane capacity for uniaxial bending members. The first one is the compression members. So if you have a compression member and you want to check the out of plane capacity, out of plane capacity means bent about its minor axis or y axis. So in plane about x, out of plane usually about y. So a member subject to a design axial force in asterisk and design bending moment mx about its major principal axis and will buckle laterally shall satisfy the following. Okay, so what this mean? We have a column that's already under bending moment about its x-axis. Okay, but this column will buckle about its y-axis. So the column, due to the load, will be buckling about y. So this is buckling about its minor axis. Okay, so here in this case, we are considering the buckling or the bend about its minor axis. So in this case, the formula mx asterisk should be less than or equal to phi mox, where phi, again, 0.9, and mox is the nominal out of plane member moment capacity. So here, this is the out of plane member moment capacity and will be calculated using the formula mbx multiplied by 1 minus n asterisk divided by n asterisk over phi n cy. So mox, O for out of plane, mbx 1 minus n asterisk divided by phi n cy. MBX is the nominal member capacity without full lateral strain. So MBX, we have found earlier the member moment capacity as a flexure member. Okay, N asterisk is the design axial force. NCY, what is NCY? NCY here is the nominal member capacity in axial compression as a compression member. So NCY is the nominal or the member capacity in axial compression. This is compression member we done earlier in the course. So it is like mix between the member capacity for bending moment and member capacity for axial load. The next case is if we have, and the one note here, guys, this case are not for one column. This case is a possible cases we may have when we design a frame column. So we can't have all these cases at once, but we just need to, sorry, we just need to check based on our case. Okay, so the standard or the lecture slides give us all the possible cases we may have in designing a column, a frame column. So the next case is uniaxial member, uniaxial bending member, but the force is tension force or tension member. The axial force is tension. So in this case, for tension members, we should check, and if we have a member under axial tension N and design bending moment X about its major axis, so the buckle laterally will follow or will need to be checked against the following formula. Mx asterisk should be less than or equal to phi mox. So here, same formula here, but the difference will be what is MOX for attention member. Okay, so in this case, again, phi equal to 0.9. MOX is the nominal out of plane member moment capacity for a tension member. Here in MOX will be equal to MOX equal to MBX times 1 plus N asterisk over phi NT and should be less than MRX. So here we have plus because the force is tension axial load. And the maximum limit for this is MRX, where MBX is the nominal member moment capacity and NT is the nominal section capacity and axial tension, and MRX is the nominal section moment capacity reduced by axial force, and we have calculated this one earlier in section point 8.3.2. So NT section capacity and tension, and MRX is the section moment capacity after considering the tension force. Okay, so this another case for uniaxial bending. Now the last two cases are if we have biaxial bending for compression member and for tension member. So for biaxial bending, again, what this means? This means that we have N asterisk and M axis, MX and MY. So everything we have at once. So if the member under compression force, this means that N is compression. The biaxial bending member capacity will be following this formula here. So the formula is mx asterisk over phi mcx plus my asterisk over phi miy to the power 1.4 both should be less than 1. Okay, so phi is 0.9, mcx is the lesser of the nominal in-plane member capacity MIX and the nominal out-of-plane member capacity MOX for bending about major principal axes. So this means that MCX is the lesser of two, MIX and MOX. What is the difference between MIX and MOX? What is the difference, guys? MIX in plane capacity, MOX is out of plane capacity. So you have two capacities. You will take the critical. The critical is the less. Okay. For MIY, I means in plane. So nominal in plane member moment capacity determined in accordance with clause 8.4 for bending about minor principal axis. So here we have MIY only one value, which is in plane member moment capacity about y-axis. So this is our MIY, in plane member moment capacity about y-axis. So if we go to our in plane, so here in plane capacity, so you will find it using this part here. Okay, so MI will be nominal in plane member capacity, MS times 1 minus N asterisk divided by phi in C. So what this mean? This means that MIY here, just write it here, M equal to MS times 1 minus N asterisk divided by phi in C. This general. So if this Y, this should be NCY. Okay, so MIY is the nominal in plane member moment capacity for bending about y-axis. NCY is what? Member capacity of axial compression for buckling about y-axis. Okay, so this is how to find MIY. Now the last part is if this member is under biaxial and it is a tension member. So again, N asterisk, MX asterisk, and MY asterisk. N asterisk is tension force. So the member capacity of this member will be almost same formula from the previous slide. So we have mx asterisk over here, it is phi mtx, and here it is phi mry. Okay, so the previous one was phi mcx, here phi mtx, C for compression and T for tension. So phi is 0.9. MTX is the lesser of the nominal section moment capacity MRX reduced by axial tension, and the nominal out of plane member moment capacity MOX determined according with these two clauses. So again, MTX has two values. We will take the lesser of one of them, the lesser of them. So the first one is MRX and second one is MOX. So we have here MTX. We will find two values and find the lesser of them. MRY is the nominal section moment capacity reduced by axial tension determined according with clause 8.3.3. So MRY is the nominal section moment capacity. So MRY, if we go up, 8.3.3. Here is MRY. So MRY can be found using this formula or this formula here. So MRY equal to this value, MSY. Okay, so MRY equal to MSY times 1. Here it will be plus because the force is tension force. Is it correct? Multiplied by N asterisk divided by phi NSY. So this is the value for MRY in this case. Okay, I think that's all for today. Do you have any question, guys? Any question? Not good? Okay, thank you for attending all. I will see you soon. Thank you.